Assalamualaikum and good day. Now we continue with the week 15 part 2 lecture. Okay. Similarly, I will explain using the module because not all of you have this module, and for slide you can always refer to the slide. Okay, for this chapter it have a lot of reading. Okay, when it have a lot of reading means that there is a lot of term that you need to understand. Okay, don't focus on memorizing, because if you focus on memorizing too much without understand, you will have a hard problem in the if the question got twisted. Okay, so I will do summarization, okay, because it's long of sentences. Okay, we just go to like I'm going to do summarization. Okay, so I hope like this you can see the full view of the pages. Okay, so this is the best as I can do, and I hope it is still okay for those that doesn't have the module. Okay, so now we go about programmable logic chapter 15. Okay, so logic circuits implement using TTL chip tend to be limited in complexity. When a printed circuit board contains too many chips, reliability decreases as many components and connection may go bad. To reduce the number of components on a PCB, complex design may be implemented as chip. Okay, so this custom IC, or sometimes called as application specific integrated circuit ASIC, is one of the methods to implement complex design. Okay, now a custom chip fabricated in CMOS technology easily accommodate thousands or millions of gets. Okay, the disadvantage you can see here. Okay, now you can keep on reading here. Okay, now I'm going to go to here. Okay, programmable logic device, PLD. Okay, or field programmable device, FPD. Okay, by the word itself, okay, the field programmable device mean that it can be programmable outside the factory. Mean outside the factory that manufacturing it, means we can the designer can program it. Okay, so here explain the term field program refer to chip that leave the factory as blank. Blank is without, means that we don't do any programming to it, and must be programming by the designer outside the factory before use. Okay, so you can see this main benefit of PLDs. Okay, you can read yourself there. Then we go to the next page. You can pause the screen, okay, to help you to read properly for those that doesn't have the module. Okay, since PLD okay, since PLD often replace several other special purpose device, the design usually has fewer components, and this reduces PCB assembly test and repair cost. Using PLD, programmable logic design device, also means few parts needed, okay, to be stocked, and this reduce inventory cost. I think this is logic because it can be individually programmed. Okay, so this one means is understandable. Okay, since more of the logic is integrated into each circuit, the number of interconnection is decreased, thereby increasing the reliability of the products. Okay, this is the disadvantage of the PLDs. Okay, and then if you notice later on, each of the figure I put highlight here, it helped me to remind, to show to those that doesn't have module the figure, okay, directly, because those that have the module, they can flip the pages, but for you guys, when I explain, you need to see the page, the figure directly for those that doesn't have module. So I make effort to actually highlight. Okay, so figure 15.1 categorize the various type of PLDs. Okay, programmable logic device. So we have SPLD, which is a simple programmable logic device, which consists of ROM, PLA, PAL, or GAL. Okay, so what is PLA is programmable logic array. PAL is programmable array logic, and GAL is generic array logic. Okay. With each device typically holding less than 1,000 gates, CPLTs and FPGAs are more complex device containing up to millions of gates. Okay. Figure 15.2 shows the general configuration of the ROM, the PLA, the PAL, and GAL. Okay. Note that the fixed and array in a ROM is implemented using N-to-N decoders. Okay, you see they are using N-to-N decoders from this figure 15.2 for the ROM, for the PLA, and for the PAL, GAL. Okay. Maybe I should put the clip here so that it will help you to read much better for those that doesn't have the module. Okay, I hope it's okay here. Okay. Sorry. Okay. So in section 14.2, you already learned about the ROM. Okay, I don't want to repeat. Okay, you guys can read. Continue here. Okay. Now we go to the section 15.2, which is the PLA. PLA stands to what? Programmable logic array. Okay. So this is the history. Okay. So actual PLA consists of NAND and NOR gate. Okay. PLA is customized by making or breaking the connection among the gates. Okay. Customized. Here you see it is a customizable, whether to make or break the connection. That's how we program it. Okay. The PLA approach advantages when, okay, you can see here. Okay. The main drawbacks of PLA were their relatively high price and poor performance. To overcome these weaknesses, programmable array logic (PAL) and generic array logic were developed. Okay, you can see PAL, programmable array logic, is the improved version of the PLA. Okay. Because it overcome the weakness of PLA. It's look like the same, but they are not the same. Okay, programmable array logic and the programmable logic array. So hope you guys can differentiate that. Okay. So example, implement the following function using a programmable logic array. W equals to A plus B bar C, X equals to AB plus B bar C bar, Y equals to AB plus A C bar, Z equals to A plus B bar C bar. Okay. So solution, first we try to see if there are any shared terms. Okay, if you notice, okay, we among this, okay, function, we shade A, okay, we shade AB, and we shade B bar C bar. Okay, so first we need to look for the similarity. Okay, therefore even though there are 8 product terms, 1, 2, 3, 4, 5, 6, 7, 8 product terms, only 5 AND gate will be required. Why? Because we're going to use the shade. Okay, mean the shade term will be the shade term will be utilized. Okay, so we will use fewer AND gates, okay, which is 5 instead of 8. Okay, so the circuit is shown in figure 15.4. Okay. Okay, sorry, I didn't show just now. So the programmable logic array PLA was introduced in the early by Philip 15.3. Okay, so 15.3 will show the looks of PLA. Okay, but this one is 15.4 is how we're going to solve this solution. Okay. Okay, I adjust it so that you guys can see. Okay, you guys can see, inshallah, I hope. Okay. So this is the general configuration of the PLA. Okay, so you have the programmable and array, you have programmable or array, then you have D3, D2, D1, D0. This is the general configurations. Okay, so this is to answer the question, the example just now. So you see, we have a shared term, right? The A, the B bar, sorry, the A, the B bar, C bar, okay, B bar, C bar, and then what else just now? In AB, okay, in AB. So the shared term. So you see, instead of using 8 get, because of 8 product term, we just need to use 5. Okay, so you see the shared terms. Okay, how minimization can be used. Okay, okay, so I just open again so that you guys can see. Okay, the A, AB, and B bar, C bar. A, AB, B bar, C bar is shared. Okay, so that's why we just do common terms. Okay, common terms, and then burn accordingly. Then you see this is the W, X, Y, and Z function. Okay. Okay, enough with that. Now we go to the next pages. Okay, so PAL, programmable array logic, and generic array logic. Okay, so PAL was introduced by monolithic memories. Okay, this is history, I don't care. PAL provide array of programmable and logic, but the OR condition are fixed. Okay, you see here, PAL provide an array programmable and logic. Okay, you can only program the AND gets. However, the OR conditions are fixed. Okay, as shown in figure 15.5. Okay, so programmable AND get, OR get, fixed. Okay, so okay, so now we go to the figure, corresponding figure 15.5 to see the programmable array logic. So figure 15.5 here. Okay, so what does it say just now? Programmable AND get. Okay, here programmable AND get, and fixed OR get. Okay, you can see it is fixed, you cannot do anything to it. Okay, so this is where you can do a customization. Okay, because it's a programmable and array. This is your PAL or GAL general configuration. Okay, okay, because PLA is simple than PLA, it is cheaper, then faster. However, PL is not flexible because the OR plan is fixed. This one is understandable, right? Okay, now we go to the next GAL. Okay, GAL has the same basic structure as PAL. However, it is EPROM based, EEP ROM based, so it can be erased and reprogrammed. Okay, in comparison with PL, based on fused technology, making it a one-time programmable OTP device. Okay, so this one you can see the main difference. Okay, between PL and GAL. Okay, first this GAL, okay, this GAL can be erased and reprogrammed. However, the PL, okay, only can be programmed one time. Okay, so if the question asks you what is the difference, I hope you guys can differentiate, right? Okay, GAL improve upon PAL in 3 aspects. Okay, so you guys can see this. Okay, third, GL has a programmable output stage or macro cell as shown in figure 15.7. The macro cell has this option: feedback to enable product term to be expanded, complementary output, tri-state, okay, tri-state output, and register output. Okay, so we're going to see the programmable output stage or microcell, okay, in figure 15.7. Okay, the looks of GAL. Okay, so this is your GAL architecture. You can see the macro cell. Okay, then you can see the inputs and output pins. You can see this output only pins, input only pins. Okay, I hope this is clear for those that didn't have the module. Okay, you can pause the screen so that you can see it clearly. The microcell allow a single GAL chip to perform the function of many different versions of PAL. This reduces inventory cost and enhances design flexibility. Refer to figure 15.8. Okay, so it can perform many functions, okay, of many different versions of PL. So of course, when it able to perform many functions, it will reduce inventory cost because it can perform many jobs. Okay, then you don't need a lot of chips. Okay, and enhance design flexibility. Now we see figure 15.8. Okay, so this is the macro cell internals inside the GL. Okay, so you have a gate, then you have the what, D flip-flop, am I correct? Then you have a multiplexer, then you have multiplexer, then this output. So this is the macro cell internal of this. Okay, inside this is this. Okay, SPLT are available only in small size, which limit the complexity of circuit that can be implemented. Bigger logic circuit are realized on CPLD and FPGAs. Okay, so next, okay, how I because if I if the camera is very far than the book, then the word will be smaller. Okay, it's very difficult for you to read those that doesn't have module. But if I too near, it be clear. However, it will not cover the whole pages. Okay, now we go to this CPLD. Okay, CPLD stands for complex programmable logic device. Okay, FPGA is field programmable gate array. So field programmable means you can program it outside. Now CPLD is a collection of individual GAL like PLD on single IC. So it's a collection of individual GAL, means you have a lot of GAL inside this CPLDs. Okay, on a single IC with programmable global switch matrix as shown in figure 15.9. So we go to page of figure of 15.9. So this is a basic architecture of complex programmable logic device. So you have this PLD, PLD, PLD. You have a lot of PLD here. Okay, PLD, 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 global switch matrix, and you have input, output. Okay, input, output here. Okay, I think it's understandable. Okay, so it's a collection of individual GAL like PLD. Okay, so you guys can read here. Okay. Most CPLB contains a few hundred macro cells. For larger circuit, designer tends to use FPGA. The Altera Max 7128 in figure 15.10a is a typical CPLD. This chip contains the equivalent of over 2,500 gates. So this Altera Max 15.10a is a typical SPLD. So 15.10a here. Okay, Altera Max 7128 CPLD with over 2,500 gates. Okay, B is Altera Flex 10K20 FPGA. This one is FPGA, okay, with over 20,000 gates. So Altera CPLD and FPGA chips. Okay, so the field programmable gate array is newer than CPLD. Okay, so the Altera Flex chip is shown in figure 15.10b as example of FPGA, as you guys can see, right? Okay, the chip contains the equivalent of over 20,000 gates. Okay, FPGA comprise thousands or millions of logics called configurable logic blocks CLB, arranged in large matrix as shown in figure 15.11. Okay, so we see first 15.11. Okay, so this is your basic architecture of FPGA. You have your input output block, you have logic block, you have interconnect resource, okay? And you have CLB, they call it configurable logic blocks here, okay? Configurable logic blocks inside it, okay? So hope this okay. So this one is interconnect resource, okay? In case you guys cannot see it clearly, interconnect resources. Okay, where were we? Okay, the logic blocks are connected by programmable routing channel. Each logic block is much simpler compared to GAL-like block. Okay, so each block, okay, each block inside this FPGA is simpler to compared to the GAL-like block used in CPLD. Used in CPLD. Okay, so a lookup table LUT. Okay, a lookup table LUT is the most important part of each logic block for FPGA. Each lookup table contains a storage cell that implement a small logic function. Okay, so in example, in figure 15.12, okay, we can see in figure 15.12, the 4 input lookup table can implement any variable function. Lookup table of various size may be created. So where is our 15.12? Okay, so this is our 15.12 simplified view of configurable logic block CLB internals. Okay, what is the internal look like? Okay, so we have YQ, we have multiplexer, we have clock, enable, set, reset, and we have 4 input lookup table A, B, C, D. Okay, the 4 input lookup table, okay, can implement any 4 variable function. LUT of various size may be created. In figure 15.13, a 3 input lookup table implement the function of f equals to a plus bc. Okay, so later on the figure 15.13 will show us a 3 input LUT where it implement this function of a plus bc. Okay, here, okay, you can see this lookup table. FPGA is mainly lookup table, so you have f equals to a plus bc, right? So a plus your bc, the required function, okay, and then this is your 3 input lookup table. Then you do this truth table accordingly to satisfy this y equals a plus b, a plus bc. Okay, then you have this 3 to 8 decoders. Okay, you can see accordingly. Okay, I think you guys quite this is quite straightforward and you guys can understand, right? Okay, in order to satisfy the function of f equals to a plus bc, okay, those that didn't have, you can try to pause the screen and to solve it. Okay, here I don't know if it's clear or not. Okay, here is, this is 0 0 0 1 1 1 1 1. Okay, this one is 0 0 0 1 1 1 1 1. Okay, I speak this for the sake of those that didn't have module. Okay, both CPLD and FPGA are very popular for fast prototyping. Logic design using SPLD or FPGA rely on the same software. For example, the Quartus. Okay, the Quartus is an easy to use software programming for programming device from Altera. 4 basic steps in using CPLD and FPGA are, okay, refer to this figure 15.14. This, okay, 4 step in using CPLD and FPGA, okay, which is your design entry, your synthesis, your place map and route, and device programming. Okay, so I hope you guys can read this yourself. Okay, otherwise it will be longer. Okay, so the design entry, what does it mean? The synthesis, place map and route, device programming. Okay, CPLD and FPGA share the same design flow, but they have several differences between the CPLD and FPGA. For example, first one, CPLD contains few thousand complete chip, while FPGA may contain up to million, so FPGA can have more. Okay, CPLD is better for simple design. FJ is better for more complex application. Okay, I think it's quite straightforward. Okay, it's like FPGA is superior. CPLD is EPROM based, meaning it is non-volatile and ready to use on power up, while FPGA is SRAM based, needing some time to load the bitstream before it can be used. Even though using SRAM look like disadvantage, it has the benefit of allowing FPGA to be reprogrammed. So your FPGA can reprogram while the circuit is operating. Okay, while the circuit is operating, we can reprogram it. So it is a advantage. Okay, such a circuit is called reconfigurable hardware, because while it's operating, we can still do some reprogramming to it. So it's a bit the advantage of FPGA. Okay, and the advantage of its CPLD is cheaper, of course, than FPGA. So delay are much more unpredictable in FPGA. This is the advantage of FPGA. Okay, most FPGA have higher logic function like adders, multipliers, and embedded memories to accelerate mathematical function. This make FPGA more suitable for computer-based applications. Okay, so I hope this is quite clear, this page, for everyone. Okay, so I stretch it a bit so that it look flat, easy to read. Okay, then we go to the last pages. Okay, the PLD configuration memories. Okay, so this one you guys can read on your own. Okay, and understand. I don't think it's really difficult. Okay, and this is the corresponding exercise. Okay, so I think the exercise is also quite clear from this camera view. Okay, so with that we finish chapter 15 for programmable logic. Okay, I try to make the video shorter, if you notice, because some commented to me that my video is too long. Okay, so we try to satisfy everyone, but of course we cannot satisfy all. Okay, because some will comment my video too short or too fast. Okay, when I make it short, but when I make it long, some will comment it is too long, boring, or because too long, we need more time to see it, something like that. Okay, so in the end I cannot satisfy everyone. I just try my best. Okay, so you can try the exercise on your own. Okay, or maybe in group. Okay, it's up to you. Okay, unless I stated it is compulsory to submit. Okay, so for now you can try your own. Okay, the exercise. So with that, assalamualaikum and see you soon.